Let's talk about power series. In this video, I'm going to work through the problem you see on the screen here, which is asking us to use a power series to approximate this definite integral to within 0.001. All right, so here's what we're going to do in general before we dive into the nitty-gritty. So we're going to make a power series for the integrand. So 1 over 1 plus x cubed, instead of seeing it the way it is, which is very difficult to integrate, we're going to turn it into its power series representation. When we do that, essentially we're turning this function into an infinite polynomial. So we know that we can always do the antiderivative from there. So from there, we'll do the antiderivative, and we don't have to worry about any fancy integration techniques. It'll just be a bunch of reverse power rules. Then we can do plug, plug, subtract. Even though it's going to be an infinite polynomial antiderivative, we can still theoretically plug, plug, subtract. I'll say plug in for that step. Okay, so here's the key. Once you get all the way down to this step here, this is always how we're going to start problems like this. What tends to happen most of the time is that once you plug your numbers into your antiderivative, you have an alternating series. Just a regular old alternating series from test 2. And we are going to use to make the final leap here the fact that for an alternating series, as long as it's convergent, we'll have to double check that along the way. As long as it's convergent, we have that the absolute value of the error of the nth partial sum, so Rn, is going to be less than or equal to the magnitude of the first excluded term. So we're going to use that fact from way back when to decide how many terms of this series we actually need to add up for our error to be less than that desired threshold. Okay, so let's dive in. It's not nearly as bad as it seems at first. All right, so 1 over 1 plus x cubed. The quickest way to get the power series representation of this is to see it as it relates to 1 over 1 minus x. So we can rewrite this as the integral 0 to 0.2, 1 over 1 minus, and we'll say, okay, this is negative x cubed being plugged into the classic 1 over 1 minus x. Okay, so we can put negative x cubed into the power series representation. For the regular one, it's 1 plus x squared and so on. So we'll put that guy there. So still the integral 0 to 0.2. 1 plus what I'm plugging in plus what I'm plugging in squared, and then cubed. And then I'll switch to the dot, dot, dot from there, and we just have a dx way at the end. Okay. I do want to get to an antiderivative here, but I'm going to clean this up a bit before I do. I'll simplify these terms, and then we'll do an antiderivative. So that's 1 minus x cubed plus x to the 6 minus x to the 9, and so on. You can see at this point, this is where that alternating series starts to show up. We're seeing the alternating happen here. All right, and now I can do antiderivatives for each piece. So the antiderivative of 1 is x, and then I'm going to have, let me say, x to the 4th over 4, x to the 7 over 7, and so on. And again, at some point, we switch to the dot, 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 we get the pattern across. And this is all evaluated between 0 and 0.2. So I want to pause here. I do need to get to the plug-in, the plug subtract step. Before I do that, though, I want to just make one quick check about integral convergence. When we're plugging numbers into power series, we always need to be sure that we're plugging something in that's within the integral of convergence, because otherwise we've created a divergent series and it's not particularly helpful to us. So for this classic 1 plus x squared power series for 1 over 1 minus x, we know that the integral of convergence is -1 to 1. Plugging in something like negative x cubed does not change that interval of convergence. So right here, our interval of convergence is -1 to 1, or you can say the radius of convergence is 1. We have a theorem in section 11.9 that tells us you can integrate a power series the way that we just did in this last step, and then you maintain the radius of convergence, not necessarily the symbols at the edges, but the radius. So at the very least, the interval of convergence for this power series is -1 to 1 with parentheses as well. So we've maintained the radius of convergence. The center of this power series is still 0. So that means 0 and 0.2 and everything between them is definitely within the interval of convergence. If this upper bound was outside of that, right, if this was a 2 or a 3 or something, then we would have trouble. So this is a small number on purpose, so that we're assured it's within the interval of convergence versus. Okay, so plug, subtract. We're safe to do it, so let's actually do it. All right, so with a 2 in here, or sorry, 0.2, I have 0.2 minus 0.2 to the 4 over 4, plus 0.2 to the 7, and so on. And again, I have to have the dot there. This does go forever officially. And then I'll subtract all of this with a 0 in it. And what's nice is that with a 0 in it, clearly every term is 0. So I don't really have to worry about a second power. Okay, so now we have created the alternating series, right? There's no x's anymore. This is just a regular old school alternating series that I kind of predicted in these steps up here. So we said, okay, for an alternating series, as long as we know it's convergent, which we do, right, from our discussion about the ROC, the error of the nth partial sum will be less than the first excluded term. So I need to pull out a calculator and figure out the magnitude of these terms. And it turns out that they get really small really quick. If you throw them in a calculator, this one is 0.0004. And then this one's really, really teeny. It's 1, 2, 3, 5 zeros before you get to a number. So we're looking for the first one of these whose magnitude is less than this 0.001. And that's actually the second term here, right? 0.001 is bigger. So we're saying that this can be the first excluded term, which means the partial sum is just the 0.2. So we're going to approximate it with the first partial sum, which is 0.2.